So let's look at our first example. It says, let B consist of polynomial vectors, P1 and P2. And P1 and P2 are actually labeled below, or fleshed out below. P1 is the polynomial vector 6 plus 3x, and P2 is the polynomial vector 10 plus 2x. B prime, which is the new basis, consists of the P1 prime and the P2 prime. P1 prime is the polynomial vector 2, and P2 prime is the polynomial vector 3 plus 2x. They want us to find the transition matrix from B to B prime. So what they're looking for is P sub B to B prime. And I'll modify the formula from the last page as follows. This is going to be calculated by looking at what the coordinate vector of P1 is relative to B prime, turning that into the first column, and then there's going to be a second column, and no more than that because there are just two polynomials in each base. So the second column would be P2 relative to the basis B prime. And we're going to calculate each of these columns. Let's start with P1 relative to B prime. I'll make a little workspace for that. To figure out the coordinates of P1 relative to B prime, we have to figure out what linear combination of the polynomial vectors P1 prime and P2 prime would give us our polynomial vector P1. So it boils down to this. How many copies of P1 prime added to how many copies of P2 prime does it take to get the polynomial vector P1? And what we can do is actually jump to an augmented matrix to help us solve for C1 and C2. And here's how you'll construct this augmented matrix. In the first column, we're going to populate it with the coefficients of P1 prime. Now, if you look at P1 prime, we could rewrite 2 as 2 plus 0x. So the coefficients of P1 prime are going to be 2 and 0. And so that's how we populate column 1. What's going to go in column 2? The coefficients of P2 prime. Yep, which are 3 and 2. You got it. And I'm going to augment this with the coefficients of P1, which are 6 and 3. I'll provide the RREF version of this matrix. Then I'll give you a shot at this with P2 relative to B prime. You get the 2 by 2 identity on the left, and you get these two numbers on the right, 3/4 and 3/2. Now, what do they represent? Well, they represent the values of the coefficients. This tells us that C1 is 3/4 and C2 is 3/2. Therefore, the polynomial vector P1 relative to the basis B prime can be written in column vector format with these two values, 3/4 and 3/2. And this is actually going to be column 1 of our transition matrix. I'm going to have you folks take a few minutes to work on column 2, which is given by the coordinate vector of P2 relative to B prime. All right, and you can pretty much emulate the work that we just did for our first column. All right, so I'll give you a couple minutes to work on that, and then we'll go over the results. All right, so let's go over this part. Pretty much the same setup as the first column that we calculated. You're really trying to solve a linear combination, namely solving for the coefficients of p1 prime and p2 prime that give you p2 this time. Which you can set up in an augmented matrix format. You would find that you actually use the same four numbers on the left. Yeah, you can call it C3 and C4. Yep. And then the second column would be 3, 2. And then to the right of the vertical augment bar would be the coefficients of P2, which are 10 and 2. I should have put 46 and 2. A nod to the Rock Band tool. But anyway, you can RREF this matrix. Get the 2 by 2 identity on the left-hand side. And to the right of the vertical bar, I was getting 7/2 and the number 1. All right, confirmation on those two values. So 7/2, cool, thank you. So 7/2 is our value of C1, or C3 in your case, Tommy. And then 1 is our value of C2, or C4 in your case. Either way, we do have our second column of our transition matrix, which are the coordinates of P2 relative to the basis B prime. I'm going to write that in column vector format, much like the first one. And there we have it. We'll finally put together our transition matrix, which takes us from B to B prime. Our first column will consist of the values 3/4 and 3/2. And then our second column will consist of the values 7/2 and 1. And there she be. So the benefit of grinding through creating a transition matrix is that well, you can give me any polynomial based on the basis b, and all I would need to do is convert the coefficients to a 2 by 1 column matrix and multiply by this one, and it would automatically give us the coordinates of that vector relative to the new basis b prime. So I'm going to give you guys a chance to build one of these transition matrices from scratch. It says find the transition matrix from b prime to b. This is a transition matrix that takes us from the new basis to the old, which we'll write as p sub b prime to b. And I'll get you going with this by modifying the formula from the last page. This time you want to solve your linear combination involving the polynomials p1 prime and p2 prime. So that should be p1 prime in the first column and p2 prime relative to the old basis b in the second column. Okay, so you've got two calculations to do. P1 prime relative to the old basis b, and then P2 prime relative to the old basis b. All right, and I'll be turning my mic off and giving you guys some time to work on this matrix. And after a few minutes, I'll check in to see how you did. All right. So I'm gonna just jump straight to the matrix, and let me know if you get different values, and we can go over the work for each of these two workspaces. If not, then what I'll do is include the details of the solutions of the linear combinations. But this is what I was getting for this transition matrix. The first column, -2/9 and 1/3, and second column, 7/9 and -1/6. How does that look to you folks? All right, cool. Very good. It happens to be the inverse of the matrix that we found in part A. So just a little secret. Now for part C, here's where it can get a little dicey again. It says compute the coordinate vector p relative to the basis b, where p is equal to -4 plus x. And then compute the coordinate vector of p relative to the basis b prime. And here's what I mean by where it could get a little dicey. This polynomial p equaling -4 plus x, this is based on the standard basis for Pn, which consists of the monomials 1 and x, which is why they're asking us to first find the coordinate vector of p relative to the basis b, which is the basis from the last page. Once we have that coordinate vector, we can use our transition matrix to get the coordinate vector of p relative to the basis b prime. All right, so this is kind of a two-parter. First part, polynomial p relative to the basis b. Okay, so we would have to figure out the coefficients of this linear combination, C1, P1, plus C2, P2, equaling P. That will produce an augmented matrix, in which case we would solve for C1 and C2. The coefficients of P1 are 6 and 3. Let's verify that. Yep, 6 and 3, 10 and 2. And then for P, we'll use the coefficients of -4 and 1. Now, just in the interest of time, the RREF gives you the identity on the left, and to the right of the augment bar are going to be the values -1 and 1. And what this tells us is that the coordinate vector of the polynomial p relative to the basis b is equal to 1, -1. Okay, so that's the first part. For the second part, to figure out the coordinate vector of p relative to the basis b prime, we're going to use our transition matrix. Now, the transition matrix that we should use, let's say use here, needs to take us from the old basis to the new basis. Okay, because in step 1, we calculated p relative to the old basis b. So we need to use the matrix P, which takes us from the old basis to the new basis B prime. Okay, so we'll use this matrix in conjunction with what we just calculated in step 1 by doing the following. Okay, the matrix that takes us from B to B prime had the first column values of 3/4 and 3/2. I believe this was our solution to part A of this problem, and then 7/2, 1. And right next to that, we're going to take P relative to B and do some matrix multiplication. And when you multiply these together, you get the following values: -11/4 and 1/2. Okay, so rather than going through the trouble of forming a linear combination and so on and so forth, or as a vlogger I watch, he says so forth and so on. We can just do this mixed multiplication, and it can sometimes be a lot faster. Okay, so the coordinate vector of p relative to the new basis b prime would be the product of those two matrices. I want to point some. Yep, go ahead.
Can you explain why you multiplied those two again, just instead of doing linear combination? Like why did we use the p sub b to b prime and multiply that?
Yep. So I'm going to reference this part on page 1. What this says right here is that we can get the coordinate vectors relative to a basis b by multiplying the coordinate vectors of v relative to b prime by p. And although this isn't what we're necessarily calculating in that part of the example, it's saying that if we want to convert from one basis to the next, then multiplication by a transition matrix is what you can do. And you know what, I'll make a note to the right here, maybe provide a couple of formulas. The coordinate vector of v relative to b prime can be found by taking a transition matrix P, going from b to b prime, and I'll put that in brackets just so it resembles matrix notation, and multiplying that to the vector v relative to the basis b. Now we have two transition matrices that we're kind of focusing on. We got b to b prime and b prime to b. So here's what I mean by it's easy to mix up notation. But I'll give you a little trick as to which transition matrix you would want to use. If you're going from b to b prime, the first and last b notation should match each other. So your input vectors, if you will, in this case, come from the basis b. And when you do this mixed multiplication, the vector that you get as a result lands you in the basis b prime. Okay, so this is where you end. Yep. And then you could do a similar thing if we wanted to go in the other direction. P would take you from b prime to b, in which case you would take that matrix and multiply it to v relative to b prime. And here's another instance where the first and last b notation match each other. So yeah, I'm referencing the equation here that says we can get from one coordinate to the next via matrix multiplication. Yep. I want to point out that for something like part A of our first example, we ended up using the same left-hand side in these augmented matrices. The only things that were different between these two matrices were the coefficients of the different basis vectors. Instead of duplicating some of this work, which some of this work is duplicative, you can fuse this into just a single augmented matrix, and by doing some row operations, you can get the entries of the transition matrix.